Hello again, YouTube. It is time for another topic review. If you're new to the channel, new to the playlist, I am currently a student enrolled at the coding bootcamp called the Flatiron School in the data science program. I'm in the fourth of 5 phases, and I am vlogging about what I learned along the way. And a new thing I'm doing for this phase is I'm sharing what I'm learning with my dad here. He has a background in psychology, and so this is being an interesting experience for me to explain these technical things to a non-technical, more what would you say, liberal arts? What does psychology fall into?
I guess liberal arts makes sense.
Like in sociology and like that whole side of like college.
More of a pseudoscience.
Pseudoscience. Yeah. So
we make it up as we go.
Right. So he doesn't, do a whole lot with computers, much less even write code or anything. So this is fun for me to make sure that I'm explaining things in a way that somebody that doesn't know about this stuff would understand it. So today we are discussing module 35, which is all about clustering methods. So I actually wrote a little bit of code for you today, so you'll get to see like kind of what I mean when I say like, oh, I'm running code. It's all already been ran and everything, but you'll get to see the code itself. So you've heard me talk about in the past this idea of supervised and unsupervised learning. I'm trying to get on level so your face is there. We go. So you've heard me talk about supervised and unsupervised learning before, right?
Yes.
Yes. So the big difference between the two being that with supervised learning, you need the supervised part means that it has labels. So for every like row in your spreadsheet, there's some column that's saying like, ground truth, it is this class or this class or this class, right?
Right.
So unsupervised learning is a family of machine learning algorithms that do not require these labels. Clustering algorithms is one of these unsupervised learning methods. So you can imagine if we have, I'm gonna have to come up with a better way to do this. I bet I can have this on my leg right here. Yeah, cool. So you can imagine if we have this scatter plot of data points, you could write some kind of algorithm that could identify like each cluster.
Okay.
On the plot, right? And effectively assigning labels to each one of these clusters.
And each cluster is color coded.
That's just for our purposes.
Okay, but I guess my question is the cluster that has it's like the green and the yellow, or the blue, or whatever color. Would that be labeled as one thing, or are those two separate things? That just
right. That's these would be different classes, right?
No, but the one up in the right hand or left hand.
What about it?
Are those two?
Yeah, because they're
Separate
two different
clusters?
colors.
Okay, all right.
Now, but all this data right here, I just made with this function right here. So I just told it I want 40 data points, 2 different features, so 2 axes basically, and I want 6 different clusters, and that's like roughly the variance that I want like in each cluster. So usually when you're doing clustering algorithms, you don't already know exactly how many clusters you have.
Yeah.
All right, so we'll get to that in a second. But there's 2 broad categories of clustering algorithms. The first being non-hierarchical. And in this module, we learned about a specific non-hierarchical clustering algorithm called k-means. And the k is kind of a fill-in. You see this a lot in statistics. There's all kinds of k neighbors, k means, different like k algorithms. And so the k is how many clusters we have. right?
Okay.
So these black dots right here are centroids. So what's going on here is I'm building a k-means model, right? That's right here, and then I fit the data to the k-means model, and then I have the k-means model predict the centroids, which are these black dots here, right? So you can see, like, with pretty good accuracy, it's identifying the center of like each one of these clusters. Is basically what's going on.
Right.
So problem with k-means is that you it's dependent on how many centroids you tell it to produce. Like I told it there's 6 clusters in here, so that's, if I told it there's 5, it would probably have like identified these as like one cluster. You see what I'm saying?
Right.
So there's k-means, and basically like k-means, like it will randomly assign like a centroid, and then it will move that centroid around. It'll find like the nearest data point and then adjust the position of the centroid, and then find the next nearest data point and adjust the position of the centroid. And so the centroid is kind of, as the algorithm is running, is kind of moving around until it ends up at the sort of like mean of a given cluster. So a lot of that's dependent on like imagine if it randomly assigned like a centroid like out here, like on the first iteration, then that centroid would just stay there and it wouldn't even assign any data points, so we'd have a false centroid. So you kind of have to massage it a little bit to get it to really do what you want. So there's k-means clustering, and then there's hierarchical agglomerative clustering, which is a mouthful.
Yeah.
But basically, this is a way of like subsetting your clusters or demonstrating that there's clusters within clusters. So this is kind of a visualization of the algorithm in action. So you'll start with no clusters, and then it discovers this cluster, and these two. These are just like a little bit further apart than these two. These are the like 2 closest data points, like after these, and so on and so forth. And it keeps like expanding these clusters until you get like these 3 pretty well defined clusters.
Right.
But what makes it hierarchical is that it's also remembering what those original clusters were that it made, right? So like one example of this is like the way your photo app on your phone organizes photos. It might organize it by date and then location, or something like that. So it'll cluster it by the date, and then it'll also cluster it by the location.
Okay.
So there's, you know, like a hierarchy of like features that are like more or less important for depending on like what cluster index you're kind of looking at. So a unique thing about HAC, which is hierarchical agglomerative clustering. I just call it HAC because it's way easier to say. Yeah. There's different types of things called linkage criteria that you can use, which is basically the rules that it's following, or like the things it's trying to satisfy when it decides like each one of these clusters, right? So Ward is usually the default criterion for whatever model you're using. So it picks 2 clusters in a way that the variance within all clusters increases the least. Generally, this leads to clusters that are fairly equal in size. So by variance, it's saying like, I'm looking for a good example here. Like the variance in this cluster, so you have these like this tight group right here, and then you got like a couple of outliers.
Right.
There's greater variance in that cluster than there is like say in this yellow cluster, right? Because those are like more tightly fit. So with a Ward linkage criteria, it's going to group data points together where the variance within the resulting cluster is the least.
Right.
So it'll try like a lot of different ones, and it'll find the one with the least variance, and then it'll pick that one. Average is it takes the average distance between all the data points within a cluster and between 2 different clusters, and it tries to optimize that value. And complete, it merges 2 clusters that have the smallest maximum distance between their data points. So it'll take like, say, these 2 clusters, and it'll take the maximum distance between like the 2 furthest data points, and it'll make that measurement for all the different clusters, and whichever pair of clusters has the least maximum distance, it will group them together. So that's what's happening when you have like this circle here and this circle here, and then the bigger one around it. Right. So complete and average work pretty similarly. It's just like you're kind of doing the calculation in a different order, versus Ward is just like a completely different metric. So that's one of the disadvantages of, or things to consider when you're doing HAC, is it's very dependent on like, the result is dependent on what type of linkage criteria you choose to use, or linkage, I guess. Up here, like this model worked basically perfectly because we already, like I made the data myself, so I already knew exactly how many clusters there were supposed to be. So I was able to tell it, and it performed perfectly. No surprise there. If I already knew that, there wouldn't be much of a point in using a clustering algorithm. Right? So, in the real world, what do you do when you don't know how many clusters there are already? What you do is you test different models with varying hyperparameters, are what these called. So I'm telling the model, look for 3 clusters, look for 4 clusters, look for 5, 6, 7, so on, right? And then you evaluate the performance metrics for each one of these models, and you pick the one that performed best. So you've seen performance metrics before. We're just using slightly different ones for this, but it's still the same idea. It's some statistic that we're calculating about the model to decide if it's performing well or not. So this one, the Kolinsky-Horrobs index, or also known as your variance ratio, is the ratio of the variance within a cluster, of the data points within a cluster, versus the variance between clusters. Right? So like how widely dispersed are the different clusters themselves, the ratio of that to the variance like within a given cluster. And the score, obviously you want the variance to be like pretty minimal. You want the intercluster variance, the variance within a cluster, to be minimized. You want the intercluster variance, the variance between clusters, to be maximized. So there's this formula that the computer does for me. I don't even know what the calculus notation for it is. I just know how to write the code for it, like a lot of this stuff. And basically, like the higher that Kolinsky-Horrobs score comes out, the better. So I have this list here of these 1, 2, 3, 4, 5 different models. These are all independently like their own model with their own predictions and everything. So this for loop is saying for everything in that list, do this stuff, is basically what's going on here. And the stuff that it's doing is it's getting the labels, or i.e. the clusters, from each one of those models. It's calculating the Kolinsky-Horrobs score, and then it's adding that score to this list right here, which is empty at the start, but after this cell runs, then we get this list right here. And so these are the Kolinsky-Horrobs scores for each one of those models, and it looks like the second one, which is 4 clusters, was the best fit. Now this I should have noted earlier, this is not, we're no longer dealing with this data set right here.
Right.
Yeah. I made some blobs again, but you can see here, like the centers parameter, it's every time I run the cell, it's going to spit out a new data set, and it's going to randomly pick a number of clusters between 3 and 8.
Okay.
So we don't really know how many clusters there actually are. But according to the Kolinsky-Horrobs index, there is about, what did I say, 4? 4 of them. Yeah. According to that. So another maybe easier way to read that is to actually plot it. So this line represents our Kolinsky-Horrobs score as we iterate through increasing numbers of clusters. And so you can see our performance peaks at about 4. So we want that Kolinsky-Horrobs score as high as possible, and then we get diminishing returns afterwards. So this is just visualizing this list right here,
Right. Okay.
which is obviously just you don't have to squint your eyes as much when you read the plot. So you have within cluster sum of squares. We talked about sum of squares before, so it's a similar idea, but just like for a cluster rather than a group of data points for like a linear regression. And that you actually want to decrease, but you don't want to decrease it all the way to 0. What you're trying to find is what iteration makes the biggest difference. Here again, you can see 4. After that, we get diminishing gains, but between 3 and 4, we get quite an increase. So this tells us that 4 clusters is probably ideal because we get diminishing gains afterwards.
Okay.
Does that make sense?
Yeah.
Again, it's just like some scores. There's like every model has like a bunch of different score statistics and different things you can calculate. Some of them, like the Klinsky-Robs, you want it to be high. The within cluster sum of squares, you want it to be low. But it's just, and you just kind of have to understand like how they work, because if you just went to like, this is telling us that if we picked, let's say there's, how many data points is there actually in here? 400 samples, so that's how many data points we're dealing with. According to within the cluster sum of squares, if we had 400 clusters, that would give us the least within cluster sum of squares. So mathematically, that would be your strongest performing model, but having a cluster for each data point is really it's not useful to us. It's not really grouping the data for us, right?
Okay.
So that's why you don't want to just keep going with this, because you're going to start like overfitting the model, essentially.
Yeah.
But it's this elbow plot shows us that that's where the biggest difference is made, and so that's where you would zero in on. Adjusted RAND index, whoops, computes a similarity measure between 2 different clusterings by considering all pairs of samples and counting pairs that are assigned in the same or different clusters predicted in the true clusterings before adjusting for random chance. Note that the true labels must be known to use this metric. So that's like a big disadvantage of the adjusted RAND index, is you have to kind of already know how many clusters that there are. But again, that's just another way of scoring your model. So you get these different numbers. It looks like for k-means, so we have a k-means model, and then we have like an HAC model using Ward, a HAC model using average, and HAC model using complete, like the linkage criterions.
Those 2 are the same.
Where? What?
That one that you're pointing at in the very bottom.
No.
Those numbers. Yeah.
Oh, the numbers are about the same. Yeah. But the models are different. This is an HAC model using complete linkage, and this is a k-means model. So this is a way of, once we've kind of identified, we're pretty sure how many clusters we have, then we would look at the adjusted RAND index and calculate that score, and that would kind of tell us. What I did was I built each one of these models using the amount of clusters that I discovered, and then I built like a k-means model with 4 clusters, HAC Ward with 4 clusters, and so on, and then calculated this score, and then that showed me which model performed the best according to your adjusted RAND index. So first I figure out how many clusters is probably true, right? And then using that, like keeping that constant at that point, then I built a few different models to see which model performed the best using 4 clusters specifically. Before that, I was trying to figure out how many clusters to use to begin with. Once I know that, then I just calculate, I test different models, because all these models use different, there's like mathematics like under the hood, so it's worth it to like test and see which one performs better, because you never really know.
What's the one that has k-means at the end doing differently than the one that says comp at the end?
What?
where it says labels
Yeah,
underscore k-means and then labels underscore comp.
Uh-huh.
What are they doing different?
So this was a hyperagglomerative clustering model using complete linkage. This was a k-means model.
Okay, because
They're two different models.
they're two different models, but they came up with exactly the same whatever that ratio score number is. They're exactly the same.
Uh-huh. Yeah. So that's like interesting. I would like then zero in on those two models and test other metrics, like to see
Okay.
between the two of them which
Okay.
one. Because again, you can't use just any one metric. So it's kind of this pattern of like building a model, evaluating the metrics, throwing out some models, keeping some others, and evaluating different metrics. Because yeah, obviously the adjusted RAND score can't really tell the difference between k-means and HAC with complete linkage. So now I'd have to figure out what that is.
Okay.
Another score is the Falke's Mallow score, which I think you also need. You need your labels to be known for your Falke's Mallow score. This is like a lot of statistics. It's on a scale of 0 to 1, so the closer it is to 1, the better. And this is the same thing you saw just a second ago with these same different models. And it looks like, our k-means and our complete linkage, again, was exactly the same. So that is, that's something, if I was doing like a really rigorous analysis, that's something I would take the time to investigate a little bit
Figure out
further.
what,
And sometimes it is just like it's just like a toss up between two models.
Yeah.
And at that point, if there really is no like difference in performance, then it would be like, which one can you explain to your stakeholder? Which one can you explain better?
It's interesting to me with that many decimal points. It's like how they could be exactly the same.
Well, it's all training on the same data for one. It looks like, even though the scores aren't the same, the ranks of these, like from least to greatest, is all the same.
Yeah.
Like, average is consistently performing the worst.
Yeah.
And ward right after it, and like so on.
Yeah.
So it might just be like converging on some value or something, and that's why it's like it might just be hitting a ceiling, so to speak. Rather than like actually landing on the exact same value, they might just be both like arriving at the same like algorithmic ceiling.
Okay.
I would imagine it's something like that more than they're just actually performing the exact same. So silhouette score is probably the most intuitive to me. So it'll calculate the intra-cluster distance, so the distance between clusters, as well as the mean distance to the nearest cluster for each sample in the data set. Which is basically your sum of squares, right? Or your like residuals. So this is calculating like basically like your variance within a cluster and the distance between clusters. And so you can imagine each cluster kind of has a silhouette. And it's just calculating like the size of each silhouette and the distance between silhouettes, basically. And so to me that it's clearly it's hard to optimize for this, because this is actually different from the rest of them, where
that one.
average linkage actually performed the best. But again, our complete linkage and k-means did the exact same. So, but that's like the easiest one. This is the easiest one, I think, for non-machine learning people to like understand, because we all know like what a silhouette is.
Yeah.
So that's just some examples of some different performance metrics that we can use. And you would use them again like at different stages, right? Like the Falke's Mallow silhouette score, all that stuff. You need your labels already identified, versus with your within cluster sum of squares and your Klinsky-Harab score. Those are used to identify if you have actually correctly figured out how many clusters to have. Once you're pretty confident with that, then there's different metrics you would use to determine like which model is performing the best on that given number of clusters. And there's also there's other hyperparameters other than just the number of clusters that you can adjust for.
So where in this process do you know what those clusters mean? That they what are they? I mean, where do you give them a label?
I mean, once you like have a cluster identified, then you would do your descriptive analysis, and you would look at like what features like influence a data point belonging to one cluster or another one. So like you might have like a few columns where like.
So then you end up figuring out somehow what those.
Yeah. So I mean you would look at your plot and you would go like, oh, like, you know, these data points in this cluster are there because of the values from like these features, and then you would look at those features, look at like what their scale is, like what they mean. You would go through the data with a fine-tooth comb at that point. So this is just like our visual tools. You've seen the elbow plot. Depending on the metric that you're using, it's not always going to have this shape. Sometimes it'll have like a hump, or like the other one you saw where it did like this.
Yeah.
Okay. But this is called an elbow plot. It's just an elbow plot is just a line plot, but specifically for clustering algorithms. Clustergrams, you've seen a couple of these before. Another really interesting one that's a slightly more technical way of representing this are called dendrograms. So like this big blue one represents like all of the clusters like aggregated, and then like so this cluster like includes like this cluster and this cluster, which this cluster includes this cluster also, which also includes these clusters, and so you have, it's kind of representing like the hierarchy. Because of the data that I had, it's really hard to get this to all fit on one plot. So that's one thing, is you gotta kind of be lucky in the sense that your data is good for a dendrogram. But it's like a little bit more like quantitative way of representing like the hierarchy of the clusters. So like, you know that this blue cluster captures everything from like 41 to like whatever's going like off the chart here, versus this cluster is within the blue and it doesn't include this cluster, but it does include these clusters over here, and like likewise for the rest. So if I had a bigger plot, then I could really like dig in and explore that. So some pros and cons of your k-means versus HAC. Oops. K-means is really easy to implement. It's pretty efficient in terms of computational cost. If you have a lot of features or like dimensions to your data set, it's faster than HAC usually, because it's only having to calculate the one cluster. It's not calculating the hierarchy of clusters.
Yeah.
You know, so you're not having to recalculate the same cluster multiple times, basically. As soon as an object or a data point is like assigned to a cluster, that's cannot change for the remainder of the algorithm running, even though like I said earlier, the centroids can move around, but the data points assigned to the clusters cannot change, like once they've been assigned. And the clusters are often like tighter, meaning they have less variance than your HAC clusters. The quality of the results depends on K. Again, like that's a whole like workflow in itself, just figuring out like what value for K to use, which is the number of clusters that you have. Mm-hmm. Scaling the data. So I've told you before about scaling. If you have like a feature that's like when I did the housing prices project, there was like features I had of like the coordinates of the house, as well as I had, you know, like the square footage of the house, and obviously those are two completely different measures on two different scales. Right. So you have to normalize those, and that will completely change like the distribution of the data points on your plot. So you would have to like already know that you need to scale the data and have done that in a good way before you even start your k-means algorithm. The initial starting point to your centroids have a strong impact on your final results. So if, like I said earlier, if you have like a centroid that randomly gets assigned just like out in space, it's never going to get assigned any data points. So it's going to throw off the model, because it's going to have basically a class that it's labeling that it doesn't assign any data points to. So with hyperagglomerate clustering, it's really handy to have the ordered relationship between clusters for certain types of data. Like I said, if you're like organizing photos or something like that, or if you have like a retail store and you have like a lot of products, like you might have, you know, like the hardware section, and within that have like power tools and protective. You have like different categories within the super category. So HAC is really good for that sort of thing. So smaller clusters are generally created because you'll have like your super cluster, and then you'll have like small subclusters of like 2 or 3 data points, which gives you an ability to kind of like comb through the data a little bit more finely. However, the cons are they result usually in the results really depend on which distance metric you use, and depending on how much computing power you have, you may or may not in a real world scenario actually be able to test all those different distance metrics. So also the objects can be grouped incorrectly early on, and there's no way to reassign them to a different cluster later. So that all these clustering algorithms are kind of it's just my computer. All these clustering algorithms are pretty sensitive, like in terms of like how they start off, right? If there's any like major errors at the beginning, then the rest of it's going to kind of get thrown off. So, what are some use cases for clustering algorithms, regardless of what type you're using? Semi-supervised learning is this new thing that's becoming more popular in the industry, and we don't have to read through all of this, but basically you'll have like a body of data, and you'll take some sample of it, and you'll run a clustering algorithm and use that to label it, right? And then you'll use those labels to run a supervised learning algorithm to classify the other like so far unlabeled data points. So that's becoming more and more popular now because, you know, there's just like so much data out there, and there's more and more and more of it every day, right? And so it's getting to the point where it's just like not feasible to have humans label every single class that we need for every single data set that we have. So semi-supervised learning is kind of addressing that issue. And there's all sorts of different applications for semi-supervised learning, especially when you're dealing with just like massive data sets. A little bit more intuitive or obvious use case is market segmentation. So you would, if you have like, you know, a body of customers, and then you would classify them into different groups, and this would be probably a good use case for hierarchical agglomerative clustering, particularly because obviously like there's going to be some clusters of people that belong to other clusters also, right? So then you get your clusters, and then the targeting phase, that's where you're talking about earlier, like how do you figure out like exactly what is forming that cluster. That's where you would actually go in and analyze like that data in particular. Like you would look at a cluster of data points, figure out what features are contributing to that cluster, and then you would look and you would do descriptive analysis of those clusters in particular. Or those features in particular, I mean. And once you gain that kind of understanding, then you can decide like what kind of business action to take to specifically target like one group of people versus another. So yeah, those are the two main use cases with this sort of thing, is when you're dealing with big data, doing semi-supervised learning, and when you're doing like, you know, trying to maximize market penetration or something, you would do market segmentation analysis, typically using a cluster algorithm. So, in summary, there's two main types of clustering algorithms: HAC and non-hierarchical, and then HAC, hierarchical agglomerative clustering. You can quantify the performance clustering algorithms using the different metrics like slow-ret ratio and variance ratio. When working with k-means, it's useful to create elbow plots to visualize the performance. It's just easier to read than like a list of numbers. And the main purpose of that is to discover what the optimum value for k is when you don't already know. When using HAC, there's different linkage criteria that can be used to determine which clusters should be merged at what points. Dendrograms and clustergrams are useful tools in HAC in particular. You can use clustergrams for k-means too, but dendrograms are specific to HAC. Advantages of k-means includes the implementation and speed of it. Disadvantage is that it isn't always straightforward what is the best value for k. This was, data that I synthesized for the purpose of this, so like I knew it was going to be easy to do that for. The real world, it might not be so simple to figure out what your optimum k value is. The advantages of HAC include visualize and intuitiveness. So it's easy to visualize, and from that visualization, like intuit like what's going on with like kind of like the wood grain looking clustergrams and everything. So it's easy to interpret and communicate to like non-technical people. The disadvantage is that the results vary dependent on what distance metric that you use. You can use supervised and unsupervised learning together in a few different ways, and applications of this are lookalike models, which is what you use in market segmentation, and supervised learning. So, that is my presentation for you. What questions or ideas or thoughts do you have?
Well, when I understood the clearest of what was going on is when you were talking about the photo thing, the clustering of dates and places, and then I realized that also you can ask your phone for a certain person that's identified in there, and it'll pull up the photos of that person. So I thought, okay, it's they're using something similar to what you're talking about to do all that. So that kind of gave me a pretty good picture of what you're doing here in uses, some ways it is used.
Because like, you can imagine, like as a user, it's probably like matters first. But if you're looking for a certain photo, you're first going to think about when the photo was taken. Right? You probably scrolled through your photos before, and you've been looking for one. And you go like, oh no, I took it before that one. And you keep scrolling. Or no, it was after that one. And start scrolling back. So they'll do it. Now they have it where you can zoom in and out like by date, right? And so they'll cluster it by date, and then they'll have like within each like month or whatever, they'll have like the locations, and then within each location cluster they'll have like the different people. Instead of just having just separate classes, like all the photos of a certain person and all the photos of a certain person, all this, it's it kind of is a way of like avoiding the need to compress data in a lot of ways.
Because I know on my phone, it will cluster photos without me ever asking it to. It just will pop up on the screen sometime of a vacation or something. But it won't be all of the photos from that vacation. It'll just be like a sampling or something, I guess. But
and there's some other model they're probably using to like pick out like exactly which photos to show to you.
So it's pretty sophisticated engineering of some sort.
So you have an MBA. So with that kind of background knowledge, do you have any unique thoughts or anything on this whole application with market segmentation?
I mean, I can just imagine there's a lot of uses for this with marketing products by determining what sectors and income levels and different things that certain products are more marketable to. I don't have a good picture in my head of designing a strategy, but
well, as an administrator in the business, you would tell some guy to
Yeah.
like do that for you. You wouldn't be doing it yourself, probably.
Uh,
They also, when you were in MBA school, when was that? Like the 70s, 80s?
Late 70s.
Um,
Yeah. I
so
think
back then, they didn't really like data science didn't exist like in the way it does today. You just had some niche like statisticians. In
back
academia.
then, you didn't have personal laptop computers.
Right. Yeah. But so back then, what they would do is it was more like intuition based of like how they would like group and cluster their customer base.
Well, one of the
But the
things,
problem with that is like there's really no like filter for your own bias. You know
right?
what I mean?
One of the things that I guess I've been kind of picking up on, and I'm not sure if I'm not really getting a good clear picture of why they're saying it the way they are, but they're talking about the recession and economy and things like this, and people buying different, more. They're not buying some of the clothes and different things that they may ordinarily buy. They're spending more on just gasoline and food and stuff. And then they turn around and say, but the economy, in terms of how much spending is really going on, is at a high end. And so it's not, in my mind, it's not separate. There are people out there with plenty of money that it's not slowing down any. But then there's people that all of a sudden, not all of a sudden, but have been living with a budget, but living well, that are changing their budget strategy because of it. And it seems like they're not really separating out enough to say, the haves aren't affected, but the have-nots are, and giving a ratio of who are you talking about, the haves and the have-nots, in terms of apparently the haves have an abundance of money to spend, which keeps things looking not so bad, when in fact, if the masses of the people are the have-nots, then it's worse than it looks like from some of these statistics.
Yeah, I read somewhere the other day that it's like 20% of Americans are basically unaffected by the recession, and the other 80% are significantly affected.
Yeah. And see, that gives a little bit of misleading information about what's really going on.
Right.
When you got 20% unaffected and 80% are, and you're still acting like, well, people are still buying this and doing this. Well, it's like, no, only a few are.
Right. Yeah.
But they're spending so much that it looks like it's okay.
That would be a market segmentation use case, is to like, if you have like a luxury product and you need to sell and you find yourself in a recession, you want to find that 20% of people that can afford your luxury product.
And make them, feel special that they have this,
Make it seem prestigious.
Right,
for sure.
I mean, that's what marketing part of it is.
Right. Might be more of a mom question, but I imagine there's like some application for clustering like within psychology, especially if you're in research, right? If you're trying to like, if you have like psychopathy, for example, is really hard to define, as I understand it. Like, it might be just like a family of different things that are like related rather than just like one thing, and so if you're trying to research something like that, clustering would be, especially hierarchical clustering, would be like a good way to evaluate that, I would think, because then you would have like the super cluster of like psychopathy in general, right? And then you would have like the subclusters of like different flavors of it.
Yeah, because when you do come up with a valid, I mean, a lot of people do diagnoses and they really don't use the DSM, but you have to identify so many factors that have occurred within a certain frame of time for that diagnosis to actually be a true valid diagnosis, even though psychologists across the board use those diagnoses with sometimes only one of those factors going on, and it's on paper and insurance is covering it and all this stuff. But the DSM, and so I'm wondering if there was some way that they use what you're talking about with the data science to determine the clusters and time frames and stuff that really should be used as, you know, a valid process of diagnosing.
Right. Well, even like the diagnosis itself would be, I think, a use case for machine learning. Once you have like a good model developed, then like that would be an easy way to, you every time you go into like a clinic, they have you fill out some kind of survey, right? To like get a feel for like, you know, what's your headspace and everything on that day. If you had a model where like the features in that model were aligned with questions on that survey, then once you have the model, a good one developed, which that would, you know, take a few years to collect the data and build the model and everything. But once you have it built, then those survey answers could be an input to a model, and then the computer could accurately predict, you know, if this person is depressed or not, or blah blah blah. And I imagine that like that sort of stuff, like the model could probably make those predictions better than a human can.
Probably so.
If like this contingent on if like the model itself is good, right? But there's ways to validate that, and I imagine just like because the model is going to be more consistent and more scrupulous than a person would be. You know, like a human being, there's no way to like get their kind of mean or bias like out.
Some people feel depressed and would be diagnosed depressed.
Right.
There's some people that are just a bit anxious and can't sit still, and you know when.
But it seems like depression.
Well, no, they wouldn't call themselves depressed. But if you went through a rigorous process, you may end up with a depression diagnosis. Is at the root of the behavior. So you got different behaviors.
So that would be like a hierarchical thing.
Yeah,
you would have like, you know, a cluster of like depression broadly, and then you would have like subclusters of different kind of types of depression.
And I mean that's why it's a pretty soft science, because most of it is either self-report or someone else analyzing the person based on their perception of what fits what.
And that's like the advantage with like the machine learning models is like, you know, across your whole career as a counselor, like, you know, you maybe like evaluate and diagnose like 1,000 or so people. I don't know exactly. You know, it's certainly not in the tens of thousands, I wouldn't think.
I wouldn't think.
But like a machine learning model, you could feed it like millions of rows of data. And so like, you know, you're making your diagnosis based off, you know, a comparison of like, you know, a few hundred other patients in your recent memory, versus the model is making that comparison against like thousands or maybe millions of other patients, like in its database. You know what I mean? And so it's going to, that like wisdom of the crowd sort of thing is going to kind of bubble to the surface. You know what I'm saying?
Right. Well, and also with personality test, that's one of the things that they have done is they've taken data from lots of people, but there was already a label for the person, and then they put all, and then you go take this personality test, and it's going to group your answers to match those labels of people that answered in those same ways. And so it's still, even though it's doing that, I guess, in a statistical way, it's still kind of a soft
Right.
science
'Cause
in
you're-
terms of
You're kind of beginning
how
the process.
well that really has, because again, when you take the test, you're self-reporting,
Right.
and sometimes you're totally honest with yourself because you know yourself that well,
Mhm.
and sometimes you're not because
So-
you don't know yourself that well.
So I was reading the other day. I think it was on Reddit. There's like some possibilities in the future of using smartwatches to actually like record data and classify this sort of thing. Like, obviously, it's not taking like your blood serum or anything, but like, with a strong enough model, you could find a correlation between like average heart rate, like at a certain time of day, and like depression. Or,
Oh, and they
like,
can do the galvanic skin response too. They could. With a,
So
So you
there's
got-
a lot of people that are working on trying to figure out like to get around the self-reporting issue.
yeah.
You know, using smartware
Yeah.
technology like the smartwatches to collect the data and then use that as inputs into the model to actually
Yeah.
predict like. So you might, one day you might start getting notifications on your phone of like, check out this local like mental health counseling service or something.
Yeah.
Which,
You spend 80% of your day in unconscious fear,
right, or like screen
angst,
time,
or
and
something.
screen time on particular apps. You know
Yeah,
what I mean? It's like one. I bet. I imagine that would be a pretty strong indicator for depression and anxiety is how much time you spend, and that's in that the ratio that's going to be different for each person. Because different people, I'm sure, kind of have like a different tolerance to that
oh, yeah.
influence or not.
And-
but
and-
with enough of your data recorded, if you're wearing your watch all the time or on your phone all the time, eventually enough of that data would be recorded.
So if you got certain apps or games or whatever you're involved in and it's recording all this data, it can tell you that when you play this certain app,
Mhm.
game, whatever it is, your system is in a stressful, unhealthy
Mm-hmm.
mode, or when you do this other thing, your body is kind of in a non-stress, rejuvenating.
Or you're excited
or- yeah,
instead
yeah,
of stressed.
yeah.
Because those like physiologically are very similar, excitement and stress.
Oh yeah,
but-
well, stress isn't necessarily a bad thing.
right.
Uh,
Well, excitement and anxiety are both
Yeah,
forms
yeah.
of stress.
Yeah.
Right. But yeah, being able to
Right.
classify like when you're on this app, you're excited, but when you're on this app, you're anxious.
yeah,
But when you're on that app that makes you anxious, you think it's good because it's like still stressing you out, but you mentally associated that with excitement or something. You know what I
Yeah.
mean? So yeah, there's a lot of opportunity with like the smartware technology. I think to get around the whole self-report issue.
well, it would help people to go, oh wow, I didn't realize that was
Right.
having more negativity
Uh-huh.
impact on me than.
Or like
that
even
it
it
is.
might notice like your time spent on a certain app or game has like doubled in the last 3 days.
Yeah.
And so there might be some like notification built in or something to just give you an extra reminder of go drink a glass of water and walk outside or something.
That'd be great if it started triggering, giving you data on when you get triggered on just unconscious program responses that would get you to do something that consciously you were going, I don't need to do that now. That's probably not,
Right.
because we get sucked into things
Right.
with unconscious, just programmed,
What would be really
habituated
interesting
behaviors.
is if like it's like too easy to get a hold of food these days, like with Uber Eats and everything.
Oh, yeah.
And if you were able to put like in your health app, I want to lose 5 pounds this month or something,
It could tell you.
and you start scrolling through Uber Eats, you get a push notification like, hey,
That's right.
And especially if it could like, it could find correlations between like if it's picking up other signals that you're depressed, and then it notices you're getting on Uber Eats more often. Like there's all sorts of like possibilities there.
You just brought up a whole new area in terms of I would love to see this kind of process used to help people in that way instead of help businesses make more money.
Right.
I mean, not that they don't need to do that too,
Right.
but there's not the it's imbalanced.
Right. Well, there's got to be a way. Like I was saying last time, there's got to be the way that we can make like personal fulfillment to the customer profitable.
Exactly. Yeah.
Right.
Yeah.
And that's like
Yeah.
that's the key ingredient that I think is missing nowadays.
Right.
But yeah, there's got to be a way to make that profitable in some way. Now, the whole like Uber Eats example, like the C-suite execs at Uber Eats aren't gonna like that.
No,
idea, 'cause they're gonna go.
they're gonna wait with.
But there's got to be like a smart enough business person, you know, a real entrepreneur, would be
Yeah.
able to figure out a way to make that profitable.
Yeah.
So yeah. Well, is there anything else you would like to add?
No, that was interesting. I like.
Yeah. This is cool. We're kind of, it's like, you know, starts off as a topic review and then blends into like a podcast sort of thing.
Yeah.
So it's cool.
You
Right.
gave me some new thinking, new ideas.
Yeah. Well, that is it for the vlog / podcast today. If you want to explore the GitHub and see everything I'm learning at Flatiron School, you can check out the link down below. Connect with me on LinkedIn. And if you're curious about Flatiron School itself and the programs it offers, I'll have that linked down below as well. And we'll see you again next time. I think the next one I'm going to do 2 modules together because they're both about time series analysis. So the module I'm in now is like visualizing, analyzing time series data, and then the second one is modeling time series data. So I'll probably put that in like one blog. So yeah,
All right.
that's it for today, and we'll see you guys in the next one.